in hand in Kelly and David's project. I acted as a sort of liaison between our team and the NASA coordinator. I hoped to remind Kelly and David of dates, and I gave constructive criticism before reviews.
Okay, and that is who we are. We are Team Uncharted, and if you will follow me by clicking on this sign here, teleport to knowledge space, right next to our logo, we will go to our knowledge space, and David will talk to us.
Okay, I'll just wait a second to make sure everybody makes it in here. Okay, I guess I'll get started now. So if everyone follows me just straight ahead, this is our James Webb Space Telescope display, and right here is our 3D model that was made in Google SketchUp. And if you look to the right here on these panels, you can see screenshots that were taken within SketchUp. And these colors were not able to transfer in world, unfortunately, but this looked like before it was exported and imported in world. The James Webb Space Telescope is an infrared telescope that will be launching in 2018, and it will be the premier observatory of the next decade, helping astronomers study every phase in the history of our universe, ranging from the time after the Big Bang to the development of solar systems and habitable planets. Now, if we keep moving forward, we will come across the original JWST spin-off technology display. So the original spin-off was inspired by an algorithm called the Shack-Hartman scanning system that was used originally to increase the speed, accuracy, and lower the cost of scanning the primary mirror segments on the James Webb Space Telescope. And that algorithm is now used in the Complete Ophthalmic Analysis System, or COAS, which is basically a system used for LASIK eye surgery. And this technology allows the human eyeball to be mapped much more accurately. And the strengths and we saw in this original spin-off was that its immense speed increase from times without the algorithm. And so COAS is able to perform 21 times faster and within 3 seconds obtain 4 different map measurements of the eye when it has the JWST algorithm compared to when it doesn't have it. And because these maps are so precise, the LASIK eye surgery procedure is much more effective and smaller discrepancies can be found on the eye. And after looking at the design, we decided that the only really big weakness of the COAS system is just how limited it is in its applicability to everyday life. It only works in eye health area, it does have a profound impact, but in any other medical field or outside the medical field, it does not work. So that limiting factor is probably its weakest attribute. Next, I will hand it over to Kelly, who will go through the design process information.
Okay, so if you will follow me over to begin as we're making our way there. Clearly, we've been having some technical difficulties this afternoon with the world locking up or the sound lagging or being choppy. So if something disconnects or if the sound isn't good, please process to repeat things if you don't hear them. So with that, we'll get started. The first problem, or the first task we had to do was choosing a spin-off. And we chose the James Webb Space spin-off applied to LASIK surgery. And since David already discussed the background information, we'll move ahead over to our right beyond the purple barrier to step 1 of our design process, which was identifying the problem. First, we had to identify a problem statement. The problem statement we came up with statement technology based on a JWST spin-off to advance the capabilities and improve the overall quality of life. The technology should apply should apply to employees without making any drastic changes to technologies in other industries. Now, some factors that we had to consider were the applicability of the original technology to other applications in industry and the relevance to daily life. And again, I already discussed background. Slide. So just to recap that last section, we chose the mirror test spin-off from JWST because of its wide range of other applications. When we first started this challenge was learning the details about the algorithm because we weren't sure if we would need to know the challenge. Now, follow me beyond the next purple barrier to step 2. We'll identify criteria and you'll see these small purple signs at the bottom of these slides. These are just some additional about why we chose certain criteria and constraints. For the criteria, it must satisfy an industry need, apply to multiple industries, so not just one. The quality of life must be improved with our technology, and it should satisfy economic and social interests while being affordable. The constraints are that we can't harm the environment or any living being. It has to be something unique, so it can't already be in widespread use, and it should not impose large costs on users. And we chose these constraints because we wanted to stay ethical, thus the environment and living things, and we didn't want to create any duplicate technologies, hence constraint number 4 about being unique. The reflection questions for this section, what criterion will be most difficult to meet? We thought that the criterion of being affordable would be difficult because of the nature of the spin-off we've chosen. We chose a complex algorithm, so our brainstorming ideas, while they would pay off in the long run, could be significant investments up front. And another criteria to consider was the complexity of the design. So in order to make a model of it within a reasonable time window, we had to stick to something that would be relatively easy to model so that we could, within the time allotted for this challenge, produce a detailed model. Next, we'll turn to this wall over here and look at step 3, brainstorming and select a design. And this is the fun part. So some design possibilities, I'm just going to highlight a few because we have a lot. Some of the ones that made it farther in our brainstorming process than others were using the LASIK technology and microchips by making them faster and smaller with this technology. Skin grafting surgery with lasers instead of a scalpel, which ended up not being a good idea because there's research going on in that already, and optics and solar cell production. Now, a lot of these were good ideas, but in order to make an honest and objective choice, we used a decision matrix. So we have our ideas listed in this column, criteria, and weights for the criteria. And we weighted industry applications, design flexibility, and creativity the most because those are what the criteria and constraints hit the hardest and emphasize the most. Daily life applications, ranges of use, and affordability were weighted a little bit less because those aspects can be improved upon with time with further development, while the others are more inherent to the idea itself. As I said, we used a decision matrix to give us an honest and objective view of our ideas and compare the ideas both visually and numerically. But before we accepted the decision, we needed to consider the strengths and weaknesses of the design that won, so to say, in the decision matrix, which was topographical mapping. So the strengths of using this technology for topographical mapping was that it could increase map detail with the complexity of the algorithm. It has municipal applications, which we'll discuss later, and applications across many other industries, as you can see with our 2 main target markets with government and private industry, where we have a lot of different possibilities with different companies. The weaknesses, however, I mentioned it's a complex algorithm, so we'll need to find new software for different applications, which can be expensive. It will also require new hardware for different purposes, so there really isn't a good single multi-purpose design, and that could be expensive. It requires training to operate, which might discourage some consumers, and aerospace applications, that was the major industry that we focused most on. Weight constraints might be difficult to meet with the varying hardware requirements. Now there are more details about this section around the corner if you'll follow me this way. If I'm moving too quickly, let me know and I can stop and wait a little bit. I see someone hanging out over by the decision matrix. Should I continue or should I wait for that person to come over here? Okay, I will continue. Some possible design applications I'd like to highlight are environment and forestry, geography and geology, municipal applications like utilities and emergency procedures, creating population distribution maps by combining data from topographic maps and population data, and atmospheric research. And we will discuss more of these applications in the business case in a little bit. The other designs had some promising applications, but they weren't as impactful on industry and daily life. So, for example, solar panels only apply to the energy industry, and we wanted to have something that applied to more than just one industry. So topographic mapping applies to countless areas because there are many different things you can do with it. And this is the original pencil sketch of our design, and I'm not going to spend too much time on that because we have some really nice CAD models coming up that will show you, they'll give you a much better idea of what the device looks like. Now, to reflect on this past section, we chose this design because it has many municipal and industrial applications, and some challenges that we anticipated were finding a versatile model that required minimal alterations between applications and industries. So we tried to find the most multi-purpose design as possible, but it was challenging. Now here is this is a sketch of a smaller part of that design, which again we will see later in the model gallery upstairs. Now before we move on, we have to consider the criteria and constraints and make sure our design satisfies those. So topographic mapping will satisfy industry needs like geology research and municipal planning. It will also contribute to daily life by improving public works and public safety. It will, since we focused on spacecraft and airplanes, there will be limited physical contact with humans and animals, meaning it will not harm living things. And this design is unique and is not currently in use. The only criterion that would be difficult to meet, as I mentioned earlier, was being affordable, because the costs are difficult to determine in this early age because it can apply to so many industries. So between different industries, the cost could change as the applications and requirements vary. Now, if you click on this sign, the teleport to design specifics, I will hand it over to David to explain about our design.
I'll give everybody a moment to teleport over here. Okay, I'm just waiting for everyone to get here. Do I sound okay now? Okay. Alright, is everyone ready? Okay. So I'm going to talk about the specifics of our actual device design in the next few minutes. So since the Shack-Hartman system is an algorithm and does not have any tangible physical substance, it needs a real physical medium to operate in, and that mechanical device that we've created is our topographical mapping device, in which the algorithm will work. So our design utilizes both the JWST algorithm and existing laser and camera technology to map topographical terrain. So the lasers work by basically creating an image of the terrain by measuring the distances and elevations between millions of points, and these points create the realistic contours of the ground beneath. However, this map does not actually illustrate the realistic, photo quality view of the ground. It's just dots like you see in this picture right here. It could be white dots or it could be multicolored dots. So to solve that problem, we have high quality optical cameras which basically work and take pictures while the lasers are working, and this image is eventually placed over the surface variations, and so this is how the final 3D topographical map is created in its realistic form. So the structure itself consists of 2 camera laser sets, and from now on I'll probably call this entire structure the turret. It's a rotating part, and so we have 2 of them on our device, and so each one has 1 optical camera and 1 laser, and these 2 parts move and work together and are also built to be flush with each other so that no rim or part gets in the field of view of either the laser or the camera. So both of these turrets are attached to a large electronics box that contains all the electronics, circuit boards, and everything necessary for both the operation and data reporting of the device to whatever's carrying it, like an airplane or a spacecraft. So our device has its translational capabilities. On the device are tracks that run the length of the box, and each turret can roll along the tracks. And the roller bearings, the wheels that are within the tracks, are kind of like roller coaster wheels that actually wrap around the shelf structure within this track so that it won't fall down or slip out, and it's completely encased by some sort of structural support. And also, these roller bearings have frictional capabilities and brake pads to stop the turret as it's moving along one of these tracks. Our device also has rotational capabilities, so it can completely translate in one direction, rotate, and pivot. And so this provides a wide field of view and also allows the one respective turret to move out of the way of the other one in the sense that it won't scam an area that has been scammed with the other one. So in order for electric signals and electricity go from the turrets to the electronics box, we designed this tether structure that's made from a flexible and insulating material like rubber or rubber-like polymer. And so the point of this tether is to protect the bundles of wires that connect the turret to the electronics box, and it protects them from the elements and also from getting tangled. And the tether also is flexible because we want the turrets to be able to slide back and forth without being anchored to one spot. And so these tethers are the full length of the entire box and are attached. One of our big challenges in designing this was that we had to find a way to get electricity from a rotating structure to a non-rotating structure, which was the electronics box. And with some research, we came across something called the slip ring, which basically uses wire brushes that surround the circular shape of the turret, and this can provide a constant connectivity whether the turret is spinning or not. And this is extremely valuable because if it was just wires filling this entire turret, they would twist every time the turret spun. And so this completely limits a lot of materials that are required and keeps everything working cleanly and efficiently. So our device can be positioned both on an airplane or orbiting spacecraft, and the design we're presenting now is more catered to an airplane, but with some modifications that will be discussed later, it can be placed on a spacecraft. And so in mapping using an airplane, you can map smaller areas much more closely with more detail, but the benefits of a spacecraft is that you can map a much larger area more quickly, and also map other planetary bodies. And so now I'll briefly turn it over to Kelly to talk about the materials that went into our device.
Yes, so one important thing you have to consider is materials. And if we look at this slide here, the outer layer, which corresponds with this green layer in the diagram to the right, will be thermoset plastics made by Motor Plastics. The inner layer, which is this teal layer, will be made by TAP Plastics. It's core mat, which sandwiched between two sheets of laminate. The connection point, which is this up here where it will connect to an aircraft or spacecraft, as well as the camera and laser housings or the turrets, will be stainless steel. We chose thermoset plastics because they are durable, with high thermal resistance and low cost. Core mat is a good thermal insulator that adds strength to the structure. And stainless steel doesn't corrode and it's strong, which makes it great for those exposed parts like the housings and mounting points, so that especially with the mounting point, your mount isn't corroding and weakening the mount. And we started to think about some future possibilities for our design. Depending on budget and weight constraints on this slide up here, more camera and laser sets could be added, which would mean faster, more accurate mapping. Another thing we thought about was energy recycling, which will be discussed on this slide actually. It would be a temperature control technique if we're in an extremely cold environment. We would have some metal coils right here in the diagram, and we would redirect by conduction heat from the exhaust nozzle of an aircraft through some coils into the device to keep it warm if necessary. And with that, I will hand it over to David to take you through the...
Okay, if everyone follows me into the model gallery, I will talk about the different models that we have. Some are just components of the main model, and others illustrate different principles about our design. So as you walk in, you first notice this very large model of the device, which is not to scale, of course, but it's exaggerated size is there so you can see specific details on it. So I'll point out a few important parts, like right here is one of the turrets. This is an optical camera, and on the other side of it is the laser, and same thing here because they're built the same way. Here is the track that the turrets can roll along, and this is the turret I was talking about that holds all these wires to transmit signals from the turrets to the electronics box. And here's the box with hex screws, and that's the way we're going to attach it to the actual airplane or spacecraft. So if we keep moving along, you can see a small model of the device, same thing, but it's about the same size as our real device, so it's much more to scale. And so that gives you an idea of what it's like. This model is an enlarged version of one of the turrets, so you get a really good idea of the roller bearings and how they work, and they're at the top, and so you can see how that works within track. And so some of the strengths we talked about was just how our design has a versatile field of view, and it's easy to expand. You can actually add more tracks to increase how much mapping you can do and the speed that it occurs. So this model over here shows basically the turrets exposed and show how they can easily slide in and out, and this is really useful because you can easily remove them and replace and maintain the parts. And these final two models show something called the end plate, which is designed to screw onto the end of the tracks and prevent the turrets from falling off. And lastly, we hope to eventually have our device turned into something that can be used on a spacecraft in mapping interplanetary bodies such as moons and other planets. And with that, I will hand it over to Kelly as we make our way to the business case, which is on the next. It appears Kelly has an internet problem, so if you prepare for Kelly happens, you send emergency, so I'll take it from here. We prepare until she comes back, so I'll take it from here until she comes back. So I'll go ahead and talk about the business case if you continue to follow me, and hopefully she'll come back soon. Okay, so this level talks about the business merits, basically, of our design and how we can turn it into an economically feasible device. And so it'll contribute many new capabilities to various industries, such as municipal leaders, scientists, geologists, affect geology studies, science, and even give us information about climate change studies. So areas of application we have include civil applications, natural disaster trends, environmental applications, and geology. In civil applications, city planners can do something that's called asset mapping, which basically records the resources in an area, such as is shown by this picture up here, and they basically have an idea of what's available in an actual disaster. You can see how the land has changed, what you can do to help people who have problems. And so that's extremely useful and beneficial to city development planning. And it looks like Kelly's back, so I'll hand it back over to her.
Sorry about that. I froze up on me. So, David, and the health of forest and human impact on the environment. With geology, I'm just going to highlight this one because this one we haven't talked about yet. We could put this up, this one we haven't, like the diagram, to find a safe place and on another planet. Now, medicine was an area that we didn't anticipate looking at, but turned out to be a really cool application. We can develop 3D topographic maps of the brain. Current ones are 2D, as you can see in this image. And we can help doctors diagnose conditions earlier on, which would help treat disease. Now, we looked into some future funding. I'm not to our project device that we came up with. So the first one has to do with threat detection, because could help U.S. military leaders learn about topography behind enemy lines without deploying troops. About Arctic geology with this, as well as hydrologic is essentially a technology transfer grant that we thought would be because it has so many industries it can be used in. Geomorphology looks at land use dynamics, which is sort of related to asset mapping and looking at how landscapes change over time. Now, our target markets are governments and municipalities. So we have national defense, the government-funded research like NASA or NOAA, and land use and regulation. So we could help a regulatory agency like the EPA ensure that land is being used properly in a sensitive environmental area. Our other target market is private industry. We have surveying companies, medical practices, as I mentioned before, and animation. We could use our mapping device to map human and animal features for film to improve current motion capture animation while still allow the animator to have artistic freedoms. Now, if you look on this adjacent wall, the industries and worth slide, you can see that these are multi-billion-dollar industries, with the medical device technologies being the greatest, with $454 billion market in 2014. Now, if you will follow me around the corner, we will review our strengths and weaknesses before continuing to our final reflection. Strengths are countless applications, marketability, ability to improve topographic maps. Weaknesses are that with each different application we require software and hardware changes, and it requires training to operate. Now, if you'll follow me around the corner this way, this is a Hubble gallery. We decided to honor some of Hubble's successes because the James Webb Space Telescope also acknowledged the incredible images that Hubble has produced. Now, if we go upstairs here to our final reflection, we will finish up. So the first question in our reflection was, what was the design and how does it solve the challenge? The challenge was to use the JWST spin-off technology to improve industry capabilities and improve daily life. And by providing industries and governments, as well as private industry, with detailed maps of terrain, we can add new capabilities to industry and allow for improvements in public works projects which would improve daily life. And David will take the next question in the reflection.
Right, okay. So the next question we responded to was, how did the work that you did through this challenge compare to the work that all real engineers and scientists do? So first of all, we had to really consider the criteria and constraints of the challenge, which is an important aspect of all real-life engineering, where the customer has certain desires, has certain criteria that they want to be accomplished with a product, and there are also physical constraints, environmental constraints, cost constraints, etc. We also had to generate 3D models of our design as well as images, so the others outside our team could understand what we had created. And so we learned how to effectively communicate our ideas to the public and other people, and turn something that was just in our minds into a real physical object. And finally, we got experience in long-distance communication, because like real-life engineers now, no one works in one building together anymore. There are many agencies, organizations, universities, labs that all collaborate across the country and even the world to accomplish a task. And as I'm from California, and Kelly's from Michigan, and our mentors are from Virginia, we had to do that as well.
The next question was pertaining to how the engineering design process improves technology. And this process is essential in improving technology because it's an organized way to evaluate all the aspects of a design, which leads to a well-developed, high-quality innovation. It requires engineers to look at the strengths and weaknesses and the minute details of their design, and that results in a thorough design process.
And next question we responded to was, describe one time during your work when we learned from failure. And so the incident that comes to mind for me at least was when I had made our original topographical mapping device model. I had made it in a trial version of SketchUp, and when that trial expired, I did not know you could not open the file in another older version of SketchUp, which was free. And so I discovered that I could not get that model, and I had to make it again. So this took a lot of time, but it also taught us to be more careful when making, saving our models and our resources, and keeping them safe. And next, we each responded to this differently, but when I was asked if you were to begin this challenge again, what would I do differently, I think I would have started it earlier, or at least done my work earlier, because a lot of times we were pushed at the last minute to do a lot of work, and it was stressful, and there there was a lack of sleep during the final days before certain deadlines, so it would have really helped to start earlier and do, especially the models, not the last minute.
And the way I responded was I would spend more time organizing our team notebook, which we used with Google Docs. We made it in the fall and we started, and you can see evidence in the original that the design process was followed, but it wasn't organized very well. So I actually had to go back and spend a couple hours organizing the whole thing so that in making slides for this presentation in our world was easier. And it would have been worth my time to just start out with an organized notebook, but this is a screenshot of our newly organized notebook with the design process in place.
Okay, and the next question we responded to was, how has science and technology pushed innovation? And the way we see this happening most prominently is through the entire space program itself. So while spacecraft are going out into the solar system, studying things, getting valuable science, and taking humanity out into the cosmos, we're also getting these spin-offs that we're talking about today that help us in our daily lives here on Earth in ways that many people do not realize.
And these were the last two questions we had to respond to as a finalist team. One of them was, how did you overcome difficulties you encountered? And many of our difficulties, as we found out, as we saw today, were technical, so like a bad internet connection. So we had to use pretty strong communication skills through other means to stay connected and continue to be productive. And we also had to overcome a 3-hour time difference when working and scheduling, so we really had to stay flexible and really dedicated to this project. And we responded differently to the next question, which was, what skills did you develop? And I learned just how important communication is. It's easy to forget how important that is sometimes. So we never were able to meet face-to-face because of the distance between us. So we used Facebook video calls, but had to work through frequent technical difficulties, which made communications difficult sometimes. But I came out of the challenge knowing how to stay flexible and patient when unexpected challenges arise.
And for me, I learned a lot about the intricacies of CAD modeling as well as video editing because I had worked on a lot of the editing for the videos earlier in this challenge. And also I learned for CAD modeling how to do things more quickly, save time, and also how to save things in the correct software. So that was pretty important and a valuable asset for my future. And I also became pretty proficient in using in-world software by learning how to import models and activate gravity, among other things, because this was my first time working in-world and I really had to learn the interface and how to use everything. And ultimately I was able to construct the building exterior that we're in now. So yeah, with a lot of work and effort, I was able to figure it out, and I'm happy I pulled it off. And with that, we've finished our formal presentation, and we apologize for the time this took. We had a lot of information to go through, but we'll now open up to questions that both of us will answer if anyone has a question.
David and Kelly, thank you so much for all of your hard work. Megan and Kenny, you were wonderful team leaders with this. We have no questions here from NASA Goddard, but there are a few questions from the National Institute of Aerospace. Becky, if you'd like to ask questions for Eric and Chris.
Okay, this is Eric. So did you consider weight in the design of your mechanism?
Yeah, so with regard to the weight itself, we actually did not have a chance to really study the physical volume of the materials that we were using, so a lot of it was more kind of qualitative, thinking about how it would be better, but we didn't actually come out with numerical values. But one of the things that we did was, in the beginning we had 2, 3, 4, I think even more of these turret things and tracks, and so at first we thought we needed that many to successfully accomplish our task, but we cut off like over 60% of what was on there down to 2, and we believe that saved weight immensely, and we believe 2 was the bare minimum that was necessary for the successful operation of the device.
Oh yeah, one more question. Did I miss? Did we miss where you talked about the tools you use to translate your models from CAD to in-world?
Yeah, wasn't listed anywhere explicitly, but I can tell you about that. So I first contacted the tech support people here and got instructions on how to download this software that basically allows you to convert the SketchUp files into the file that's necessary to be imported in World. And so once that was done, I was given access to this server online that had a password and everything that allows you to upload the file once it's been turned into that final form. And there's a little folder that basically shows all the models we put in here. And once it's in there, you can type in basically the name of the model in World and turn any ordinary object, a wall or something, into that model.
We do have one question here from Goddard.
Yeah, so my question is, when coming up with your final design, did you do any patent searching when finalizing the translation of the camera system? And if you did you find anything that was similar to what you guys were thinking, and did that have any bearing on your final choice for the design?
I can take this question. So, we didn't do any patent searching because that is a lengthy process, a formal patent search. But we did do some research, went to Google and typed in a whole bunch of things related to topographic mapping with lasers and personal products with topographic mapping similar to what we were designing to make sure we weren't duplicating it. And there are some related products out there, some consumer products or surveying products we found that do laser topography, but they don't superimpose it with a real color image. And that was the case that we found with just about every application we looked into, was that they were only doing lasers and they weren't combining them with a visual like we were. So adding that really elevated that process for this design. And if David, if I forgot anything, if you want to add anything, go.
I think you covered it well enough. Yeah, we're good.
Okay, last call for any questions.